Okay, so first of all, thank you, the organizers, for giving me this chance to present my work here. So today I brought something interesting about insects and the chemical world. Yeah, so when aquatic life or animals transit from water to land, so they face so many different challenges. So one of the challenges was water, how to conserve water. Smaller insects, smaller animal, this is not working. Smaller insects, they lose water more rapidly than larger animals because of their small size and higher surface area to volume ratio. So many of the insects, they have evolved some sort of mechanism to overcome this stress. So they do it by increasing their amount of bulk water or by tolerating the higher amount of water loss from their body. The third one, which is very interesting, and my work focused on the third aspect, which is reducing the rate of water loss, which is cuticle functioning. So 80% of water is lost from the hard cuticle, and remaining 20% is lost through secretions, oral secretions. So they lose like 90% of water from the cuticle. So any change in the membrane or in the cuticle, it will lead to water loss. So having a perfect blend of hydrophobic compound on the cuticle will serve the purpose. So as you can see here on the right hand side, so imagine these two cases where they have a hydrophobic layer on the cuticle, and in the next case where there is no hydrophobic layer on the cuticle. So the water permeation will be very high on the first case, whereas the second case it will be very faster. So these hydrocarbons are overlaid across the cuticle, and which help them to alleviate desiccation. So hydrocarbons are very diverse in nature. These are 4 different class of hydrocarbons. So alkane, methyl branch alkane, alkenes. So the complexity increases with addition of saturation, unsaturation, or methyl group to the structure. But when you have a alkane compound or molecule, so there is no unsaturation, and which will help in surviving desiccation. So I had a few questions around desiccation progression and hydrocarbons. Do hydrocarbon profile change during drought progression? And do the change in CHC profile map to rate of water loss? So to ask this question, I did a desiccation assay with different desiccation regime, and I exposed the flies to different regimes of 2, 4, 6, 8, and 10 hours. So you see a flat line. So when you expose flies to desiccation, in the initial period they will not die. So the period when they start dying is 8th or 10th hour window. So you see a flat line, and there is a decline in the survival, which shows something is changing on the cuticle, or maybe they are rapidly secreting hydrocarbons, or deployment of some long chain compounds are there. So I extracted CHCs from these desiccated flies of different hours, and CHCs were assayed, and I did GCMS to see different peaks. So I got 25 different peaks. So then I thought to do a PC analysis to see the separation of the profiles. So as you can see in the upper panel, you see 0 and 2 hour, and then subsequently you can see different hours of desiccated flies CHC profile. So large variation was observed in the initial period and in the end, which is 10th hour. Despite of so much of overlaps, you see there is segregation in 10th and the 2nd hour. Then I thought to do a random forest modeling to see which is the major contributor or key player which helped them to survive this desiccation stress. So from the left to right, you see the shorter chain compounds are more prominent, and as desiccation progresses, they had a shift towards longer chain length hydrocarbons. Then I thought to do how to link this with water loss. So I did some measurements, water balance measurement. I measured wet weight, dry weight, and water content. So you can see the wet weight is declining as well as water content. Dry weight is non-significant here. So what about water loss rate? It will go down or it will increase, that we don't know. So the takeaway is, so in the initial period there is no water loss, it's zero, but like in the 4-hour period you see a significant amount of water is lost from their body. But as desiccation progresses, they came to know, they realized that it is going to be stressful further. So they started synthesizing more hydrocarbon, and the key player is long chain hydrocarbons. So there is a rapid deployment of long chain hydrocarbons on their cuticle, which help them to survive harsh conditions. So with that, I will stop.
So 1 or 2 questions.
Very interesting work. I was wondering if you can tell what is the evidence suggesting a causal link between the long chain hydrocarbons and protection from water loss.
So people have done in various temperatures. So they grow the flies in different temperatures, and they have seen that at high temperature long chains are more prevalent, even in desiccation tolerant. So they selected populations for desiccation or drought condition and for a prolonged time. So they have seen that longer chain components are more in.
But that's still correlative, right? It's not really showing causation, because you're finding that they are more prevalent in organisms that have undergone more desiccation of a longer.
But
so it could be a byproduct of how the animal is responding to water loss. It may not be protective at all.
Sorry, I didn't get the questions.
Maybe I can talk to you more later.
Sure.
Okay. Thank you.
Thank you.